In this video, I'm going to show you how you can use standard electrode potential data or the electrochemical series to predict the direction of a redox reaction. We also see this as being asked us to predict the feasibility of a reaction or find out whether a reaction is spontaneous. They're all asking the same thing. So let's start right back at the beginning. We've got our basic setup for an electrochemical cell. I've got my high resistance voltmeter. It is connected to two electrodes. On the left, my electrode is going to be made of metal X, and it is in contact with an electrolyte containing X plus ions. I've got my salt bridge in place so that I've got a complete circuit. And on the right hand side here, I'm going to make that metal M in contact with an electrolyte of M plus ions. Now I'm going to start by making the left hand cell my oxidation half cell. So oxidation half cell. Sometimes that's known as the negative half cell, and it's also could be called the anode. On the right hand side, this is going to be my reduction half cell, also known as the positive half cell, and it is also known as the cathode. This is a point where it's really useful to check your past papers that are specific to the A-level paper example that you're following, so that you can really hone in on the language that they prefer you to use, whether it's negative half cell, oxidation half cell, anode, and so on. Each of these metals is in contact with ions of its solution. So let's head back up. So I've got X plus an electron going to form my metal X. Remember that these half reactions are always written as reduction. And I've got the same here. Ions of M can gain electrons to form the metal. Now these are both equilibrium reactions. They can go in either direction, but clearly when we link two half cells together, they are only going to go in one direction. The oxidation half cell is my negative half cell. That tells me that the position of equilibrium for this half reaction lies very strongly to the left. X has a tendency to lose electrons. It itself will be oxidized. X is our reducing agent. On my reduction half cell, because it is positive, I know that the position of equilibrium lies far more strongly to the right. My M plus ions have a tendency to gain electrons. They themselves are reduced. That makes M plus a powerful oxidizing agent, and we have the metal M deposited on the electrode. So, in reality, on my oxidation half cell, I have got my metal X going to form ions and releasing electrons. These electrons are attempting to flow around the circuit. If I didn't have my high resistance voltmeter in place, they would flow to the reduction half cell, where they would be picked up by the M plus ions and used to reduce M plus to M. If I'd like to write an overall equation for this, I just need to combine my two half reactions. So it would be X plus M plus. I need to make sure that the electrons balance, which they do already in these two half equations, to form X plus and M. Now, in terms of working out a value for E cell, if I had electrochemical data for these two half reactions, the overall E cell is always the standard electrode potential of the more positive take away the standard electrode potential of the less positive. Now you can talk about this in terms of either being positive or negative, but remember it's more positive, less positive, more negative, less negative, because we might be dealing completely with negative numbers or positive numbers. That should make a little bit more sense in a minute. Okay, so let's have a look at an electrochemical cell made from some real half reactions. I want us to consider a cell. It's going to be composed of two half cells. I've got silver half cell and I've got a magnesium half cell. So how do we know which one is the oxidation half cell and which one is going to be the reduction half cell? Well, this is where we need to have a look at the electrochemical data, our standard electrode potentials. So if I were to write it out, I'm not bothering with state symbols, and that has an E of plus 0.80 volts. For magnesium, it would obviously be picking up 2 electrons, and the value here is minus 2.37 volts. So just by looking at these two standard electrode potentials, I can see that the magnesium, because it is the less positive of the standard electrode potentials, is going to be my oxidation half cell. So what does that mean? That means that magnesium is going to be oxidized. Magnesium has a greater tendency to lose electrons compared with silver. So position of equilibrium lies far more strongly to the left. That means that my silver half cell is going to be my reduction half cell. So this is going to be my reduction, because it has the more positive standard electrode potential. So silver ions have a tendency to gain electrons to form silver metal, and position of equilibrium in that half reaction lies far more strongly to the right. If I would like to combine these two to write the full overall equation, what's that going to look like? Well, again, I'm going to take this half equation and I'm going to multiply it by 2 so that I have the same number of electrons. So my reactants are going to be magnesium metal plus silver ions going to form magnesium ions plus silver metal. And understand conditions, E cell is going to be the more positive. So the more positive there is the silver. So Ag plus Ag, let's put my phase boundary in. Take away the less positive magnesium, 2 plus Mg. So that's going to be plus 0.80, take away negative 2.37, and when you plug that into your computer, into your calculator even, it comes to 3.17 volts. Remember, for a reaction to be feasible or spontaneous, E cell must be a positive value, and this is nicely positive. Another type of question might ask you whether X can reduce or oxidize Y. So let's have a look at one of these. Can copper reduce iodine? Well, the first thing we're going to need is our electrochemical data. So in the exam, this would be given to you, or it would be on the data sheet. So Cu2 plus 2 electrons to form copper metal, and that's got a standard electrode potential of plus 0.34 volts. And if we look up iodine, form iodide ions, that is plus 0.54 volts. So can copper reduce iodine? So we require the iodine half cell to be the reduction half cell, which means it must have a more positive standard electrode potential for this reaction to happen. Let's have a look. Plus 0.54 versus plus 0.34. Yes. So iodine will indeed be the reduction half cell, and copper will be the oxidation half cell, because iodine has got the more positive of the two standard electrode potentials. So copper will be oxidized to Cu2+, and iodine will be reduced to 2I-. So the answer is yes. And finally, let's have a look at a second example. Predict whether copper can reduce zinc ions. So we have our standard electrode potential data for copper, and we can look the same up for zinc, and that is minus 0.76 volts. So working on exactly the same idea, if copper is going to reduce zinc ions would be reduced to zinc metal. For that to be the reduction half cell, I require it to have a more positive standard electrode potential compared with copper, and that is not the case. In this particular example, if I were to put these two half cells together, then clearly zinc would be the oxidation half cell because it's got the less positive standard electrode potential at minus 0.76 volts, and copper would be the reduction half cell. So can copper reduce zinc ions? No. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.